Okay, let's go ahead and go back to lectures then. Okay, you should see the PowerPoint slide where we left off on Monday. So what we're going to do next is we're going to talk about how the pass 1, pass 2 logic is going to work from a linker's perspective. Okay, and I'm hoping that you have reviewed what pass 1 and pass 2 of the assembler was doing, because this is going to build from that. We're not necessarily going to revisit that, although if you have specific questions, but we can address them if you have something specific. But building upon that information that we've already covered and knowledge that you've been working on, what we're doing now is we're extending that and saying, okay, over here in the linker part now, what do we need to do in a 2-pass linker as a part of a 2-pass compiler approach? So think about the same types of things that we know in a pass 1 phase. We're defining symbols, and we don't necessarily have load addresses and things like that at this point. Some of this will hopefully be pretty straightforward. Pass 1, we're going to assign addresses to all of our external symbols. Okay, and those are addresses that are known, by the control section. After the assembler is passed through the control section, it would know what they are for that control section. Okay, so then the other thing we're going to be concerned with then for the linker is going to be taking a look at some variables and data structures that are unique to the linker, and being able to manage multiple control sections. And that specifically we'll be looking at these 4 variables, or I should say these 3 variables in this one control structure that we've already looked at. Going down to the last one, the ES tab, or our external symbol table, is the data structure that we're going to use specific to the linker itself, and the linker is going to be writing to the ES tab as well as consulting the ES tab depending upon which control section it's resolving addresses for at any given time. So then looking back at the 3 variables, then the prog address is going to come from the operating system when we go to load this program, when we go to run this thing, right? And that's the starting address of where the program is going to get loaded into. The second one that we're going to be worried about is the CS8EDR, or control section address. Now for the first control section, this is usually the same value as the program address, and then subsequent control sections will have their own unique addresses beyond that. Some cases the control section address could be different than the program address. We're not going to really go into that here, but there are some times when you want the first control section to be offset from where the program itself gets loaded, and that would be some stuff if you went into an advanced discussion, or should say advanced study in systems programming or operating systems, that we would get into discussions about that. But for here, you could pretty much assume at this level anyway that the first control section address is going to be the same as the program address. And both of these again are the starting address for that particular control section. Then the third one that we're worried about is control section length. And hopefully this should be obvious as to why these are important, right? Because if we are taking this particular control section and we move it out of memory and we want to move it back into memory, or if we're trying to move it into memory for the first time when we're trying to load the program to run, then we need to know, okay, from the operating system, what is the starting address for this control section? Well, the operating system can't tell the control section the loader that, unless it knows how many bytes this control section is going to need. So the control section length is going to be information that the assembler is going to know, and it's going to be put into the ES tab so that when the operating system tries to find a starting address for this control section, it consults the ES tab for CES length, It's going to get that value, and then it's going to go look for a starting address in memory that has at least that many bytes. Then it can fill in the starting address for that control section address and do a bunch of work that you'll talk about in your CS570 class. Okay, so that's what these are about. And that reminds me, I need to change my pointers so it's a little easier to see. All right, so that's what these four are all about. The ES tab is the data structure, this table that we're creating, and then these are the three variables that are unique that we're going to manage it with. Okay, and then the process's own defined record is going to be also something that the linker is going to need in order to make this work. And you can see that in your textbook in figure 311. Okay, so that's all being done in pass 1. Now in pass 2, what we're going to take a look at then is actually do the work of actually loading it into main memory. We're also going to, okay, so we're going to do those things we just talked about. The linker had already created the ES tab. It's going to have each of the control sections defined, and we saw that here, right? So here's the ES tab where we defined, the linker had defined what each of the control sections are and symbols that it needs to know about. It doesn't have addresses yet in pass 1, but it does know the length. And then later in pass 1, as the linker is interacting with the operating system, it finds a starting address that has enough length for this particular control section. It could then fill that in and fill this in and fill this in. So we're doing all of that in pass 1. Then in pass 2, we'll start doing the actual work of moving data from the file into main memory. Okay, and we'll handle any of the relocation bits that needs to be performed, as well as linking across control sections. What does that mean specifically? We're going to evaluate each of the modification records in each of the control sections, one control section at a time. So we'll visit the modification record for control section A, and then we've got starting addresses. We haven't moved control section B and C in. Maybe we've loaded control section prog A in. We know what the addresses for the others are, so we can go ahead and visit all of the modification records in control section prog A, and then for all of the symbols for list B, end B, list C, and end C, we can now perform the work of the modification records. Well, likewise, we can also perform the work of changing the values from the modification records wherever symbol list A and end A was used in a modification record. That's local to this control section, but we said now that was dependent, or should say the assembler, when it assembled that code and generated that modification record, stated that it was dependent upon the starting address of prog A, even because these particular list A and end A symbols have absolute or direct values. And so now we have a value 4000. All the modification records that the assembler generated then have to have those addresses modified to reflect, in other words, do the addition or the subtraction of this value to be able to then create a correct direct address for that particular symbol, and the external symbols as well. Okay, so it's going to do all of that work for each modification record and each control section for each of those symbols that are in the ES tab. And then we'll read the end record for the main program. We're going to talk a little bit more about how to define a main program in the SICK family of machines, because in C and C++ and in other programming languages, you've already been introduced to the main function or the main method, and you understand how that works. And the main function itself is essentially what's going to contain that end record for a main program in those types of computing languages. Because what will happen is it's going to be the starting address, and then at the very last instruction of the main, that's where the end address is going to be as well. Okay, so when we load it up, it's typically the last one. If it's not, the compiler actually reorganizes your code so that it is. And that way it'll have that end record for even C, C++, and other programs that are compilable. But for the SICK family, it's pretty straightforward. We're going to have our main record, which is generally control section 0, and that'll be where we will find that transfer address. So when we finish doing all of our loading, in pass 2, when it's finished doing the loading, it's finished doing all the modification records for each of the control sections. It's going to find that end record for the program, which is usually in control section 0, but doesn't have to be. We can specify it to be somewhere else. And at that point, it's fully loaded. All of the addresses have been modified for the starting load address of control section prog A, prog B, prog C, and we're ready to start actually executing code at that point. Pretty cool, huh? That's the work of the loader based upon what the assembler and the linker had created, recognizing that even the loader now, the one data structure that is writable by the loader is going to be this ES tab. The assembler itself, the linker part of the assembler, actually created it, but in the case of the loader, it actually modifies that so we can make the rest of this important work contain correct data so that the program will actually run based upon the load address. Any questions so far? Okay. So one of the things that we're always doing is we're looking to do optimization. And this is something that you've been studying. You've actually had whole semesters in studying optimization when you were looking at your data structures class, your algorithms analysis classes, and even some of your other programming classes. We were always talking about how to do optimizations. It's probably a good time to insert just a little bit of discussion, and that is most of you are probably familiar with and have worked with or known people who know how to program who aren't computer scientists. And yes, you can in fact write software, you can program, you can code without a computer science degree. One of the things that the computer science degree does is it gives you the tools to be able to do things like perform code analysis, evaluate and assess data structures, determine best tools to optimize and best methods to use to optimize your code. So part of your analysis and your optimization is using these tools that you are learning in these classes that are things that typically you don't pick up when you're just coding. When you're just coding, you're successfully writing code that compiles, that runs, that makes it do things. You might even have learned some tips and tricks along the way, but you don't necessarily have, although you still could learn these analytical tools on your own, but you don't usually have those. That's one of the things that we do in the computer science program. That's one of the things that this degree is saying once you graduate with a computer science degree, is that you have understood the basics of our analysis and optimization techniques that we have, so you can build upon those and write a better program and deliver a better product as a result of being able to use these tools as part of your toolkits. Okay, so just like we're doing with coding, when we take a look at these types of things, building operating systems, building systems tools such as assemblers, linkers, loaders, we're looking at how we can do this, yes, so we can understand the work that needs to be done. That really what we're saying is understand what the requirements are for tools like this, with some examples of some tools that can do that, so that we can eventually be on, or at least understand how these tools can be optimized, which actually helps you write better code, because what's going to happen as you learn these tools and learn these optimization techniques is how to write your code such that the optimization has a better chance of generating more efficient code at runtime for your projects. So that's really the goal for understanding this. Now, some of you may actually go on teams eventually that are going to be writing your own systems tools, optimizing for your own particular hardware environments, or if you're working in cloud environments, working in optimization for those environments as well. It's very similar. It's a little bit different how the stack is made for cloud services than it is for an embedded system, but essentially they're the same thing. You have hosting services, you have linkers that are going to have to dynamically link with memory, a little bit more complex in some systems than others, but the fundamentals of it are essentially the same. It's just an implementation detail. All right, so that's worth keeping in mind as we're talking about these, because it's going to apply to you in more ways than you probably understand, because we're looking right now at a hardware system, but it applies to many instances. All right, so improving efficiency, that's why we've been focusing on that in a lot of your classes. That's really what we're trying to get across to you. So in this case, with this as an example, when we are looking at things like the ES tab, and this is a very, by the way, this example here is a very, very simplistic example of what an ES tab might look like. You'll never, well, I shouldn't say you'll never see one this simple, because you'll probably write something that's just a little bit more complicated than Hello World, but it's also not going to be an Amazon engine and farm of multi-millions of pages that are working dynamically at any given time. Those are very complex. So this is very simple, just to help us understand what it looks like with a simple system like the SICK family machine, so that as you understand this, you can then extrapolate it to more advanced projects and more complex projects. Sorry, that's what I was looking for. All right, so optimization, then efficiencies. One of the things we can do with this ES tab, this external symbol table, is create some ways for us to optimize the search in the table. Because just like you were doing in your algorithm analysis classes, you were understanding, hey, we've got these different trees, red, black trees, binary trees, and others that we're using for helping us to optimize our searches depending upon what that search structure was being built for. Well, the ES tab, as you might imagine, is going to be very large for most projects. All right, so one of the things that we're going to need to do to help this program get loaded up more quickly, because we're always going to have to be concerned about latencies due to network performance, latencies due to the hosting environment, all kinds of other latencies. Introducing latencies from just searching an ES tab is something we want to minimize. And so that's what we're going to focus on here in this discussion. All right, so one technique we can use is to simply serialize each of these symbols. Serializing them, of course, means creating a unique number that we can then reference each symbol with. Instead of doing a character array search across many symbol names, we just create a unique number for each one of those symbols, which is serializing, right? Starting with symbol number 0, to symbol number 1, down to n-1, we then can create a unique symbol number or reference number for each symbol in the table. Okay, and then use that in our modification records, and that alone will increase the performance of any search in the ES tab, because now we're simply doing an integer search instead of an array of character search, which is significantly longer. All right, so to implement that, the first thing we want to do is take a look at the control sections themselves, because when we do a search in the ES tab, that's the first thing we're going to do. Is we're going to go into this control section, and we're going to search for the control section that we're interested in, and then search for the symbol that we're interested in. So we want to create unique numbers for the control section name in addition to the symbol name, because they all are going to be searched and referenced by the linker and the loader. Okay, so we'll start with 00 be the prog address, and then 01 to be the first control section name. And then just start incrementing the integer for each of the external reference symbols that exist in there. So it's pretty straightforward to implement. And then referencing those, in other words, doing a replacement of symbol names for their numbers, unique integer ID, UID, right, then allows us to be able to do that quick search. All right, and here's an example of how that would look. Right, we would start off with prog A, and we can create its symbol prog A as a reference number 1. It's got its own unique address. Prog B, its own unique reference number. Prog C, its own unique reference number. And you're saying, wait a minute, I'm showing these now as 3 separate records instead of one combined ES tab. And that is true. To help us understand how we could do this simplistically first, if we wanted to do each control section as an independent, we could do it this way. And then we create create each of these unique numbers for each of these symbols as a standalone control section is one technique we can use. And maybe we do a 2-pass optimization of our ES tab by creating these subtables and being able to create numbers that way. See, there's a question here about mod records in the search process. Well, each of the modification records are going to use one of these symbols that had been created as an externally defined symbol. And so those symbols would be entered into the ES tab, and those are what we're going to serialize. And that's what we see in each of these subtables here. Okay, so we're going to use that to create these tables here with, and that way we can search on the reference number, the unique ID or unique reference number for each of the control sections. Now we need to generate that if we're going to do this, since we are doing this, we're proposing doing this technique. Then that means when we go to generate the object code, we need to generate our refer records referencing these unique numbers. And so we can do that by modifying the definition of our refer records. And we would do so by creating, it could be 2, it could a byte, right? We could use a byte depending upon how many external symbols we think we will have. If it's going to be within the size of a byte, less than 4,000, then we can use just a byte. If it needs to be larger, then we have to decide whether we want to make it 3 nibbles or 2 bytes, most likely 2 bytes, to reserve for this linking between the symbol name in our refer record and its unique ID or unique reference number. So we would then let the assembler do that, and then as you can see down here in the modification records, the assembler can go ahead and use those numbers instead of the symbol names. So 02 instead of list B, 04 instead of list C. We can go ahead and do that here in the modification records that we are actually generating. Therefore, instead of having to do a 2-pass on the loader, we'll just do this as the second pass in the linker to go ahead and say, let's generate these numbers with these names for this control section, and then use those in the modification records. So this will allow us to create the ES tab for the loader to use. The linker will be able to create this ES tab for the loader to use, and then the loader simply will search the table for these values to find, or I should say not these values, but these IDs to get the correct value address to replace at that location. Okay, and we'll do that for each of these control sections. There's control section prog A, where we've done that, And we'll also do the same thing for prog B, where we'll have now 2, because we'll reserve 01 to be the control section name itself. We saw that previously. And now we'll use 2, because that'll be the first symbol we encounter for the first symbol, in this case list A, which was now in the other control section, not unique to this one. But here's the mapping between 2 and list A, but we're only going to use the unique reference number instead of the symbol name here in the modification record, so that when the loader's doing the search, it can do it by the number and not have to do it by the string or array of characters. Likewise for control section prog C, the same thing, where the first symbol, list A, is now got a unique reference number, which is 2. Just happens to be the same as control section prog B, but it's definitely different than control section prog A, which, as you might recall, was actually list B. And where'd the screen go? Let's wait for the screen to catch up. There we go. Okay, so that then gets us to through the 3 control sections that enables us to now to optimize our searching by the loader, so that that can be done, because that's being done at runtime, so it's going to happen much more frequently than the assembler and linker are going to do, which is running once. It's probably worth mentioning, because we're going to see this later on in the semester when we start taking a look at the question of, do I build something at compile time or assemble time, or do I build something in runtime instead? And it's really going to come down to a cost function, just like we'll build cost functions for a lot of things that we do when we're doing analysis of our code. Is that what's the cost of doing it at build time, at assemble time, rather than at runtime? And it really comes down to, well, if you're going to assemble code once and you're going to run it once or 2 or 3 times, it really doesn't make much a difference, right? If it takes more time to do it at assembled time than it takes to do it that same amount of work at runtime, then maybe you would say, let's defer that to runtime and let's do it then. In the case of our compilers and assemblers, though, most of the time we're going to use those to compile and assemble and link our code once, and we plan to run this program many times, many times in a lot of cases. So if we can spend more time compiling, assembling, and linking our code to make it as optimized and efficient as possible for runtime performance, then over the life of this program, it's going to amount to a much larger savings by reducing the amount of work that needs to be performed at runtime and doing more of that at compile, assemble, and link time. So that's one of the trade-offs that we're always thinking about. We have been not explicitly stating that here in the semester so far, but this is time to bring that to your attention, that really that's what we're doing. So we'll be a bit more specific about that as we move forward in the chapters, so we can be aware of, why are we doing this? Why is this important? Why is it important to do now? Because you really should be thinking those questions as we propose some of these techniques. Okay? So that's the reason why we're doing this now. If we can do this now at link time, then when we go to load this program and run it, which is going to happen usually many times over and over again between compiles, then we're going to amount to a lot of savings over the life of this program. So if this program gets assembled and compiled, assembled, and linked once, and we distribute it out to 1 million users, even a savings of 1 second of actual compile time times 1 million, seconds, is a significant amount of savings to do the work now instead of doing more of this work later at, say, load time and run time. Okay? pretty important concept to get over because it's going to drive our discussions going forward on these newer technologies. Or these, I should say, these next technologies that we're going to discuss. Okay, so that's the end of chapter 3 for the formal parts of the discussion that we were putting together. Do we have any questions? And the questions can come either in the chat or raising hand. I'm watching both screens. Okay. So I emphasize in the discussions parts that I have traditionally seen students struggle with the most as far as the concepts are concerned. Chapter 3 in its entirety is testable, yes. I will be posting a study guide, if you will, this weekend. But the caution about the study guide is that those are some example questions, some example topics that I particularly want to focus on, but in chapters 1, 2, and 3, all of it, particularly here, chapter 3, all of it's going to be testable. Now, I am going to tailor my chapter 4 discussions. So as you notice, we only have 1 week of discussion for chapter 4, and it's right before the break. So chapter 4, I am going to focus your study time for that chapter more, but as far as chapter 3 is concerned, everything in 3 is testable. I just focused on what I thought were the harder concepts most students struggle with over the years that I've taught this class. As to how this exam is going to be administered, I will be finalizing that over the next 2 weeks, although I will say that it will be online. I am not looking to distribute a PDF file and have you turn in PDF files. I'm not going to be doing any distribution using email, but I will be using most likely Blackboard, but there is another tool I'm looking at as well, and once I've assessed those options, I will then post that for you so you can start preparing for that. But for the material itself, it's all of chapter 3, and it'll be the parts of 4 that I focus you on specifically. For the projects, oh yes, so the question, this question comes up as a good question here in regards to how I want you to be able, or how much detail, right? How much of these new things we're introducing do I expect for you to implement inside of this project? And I'm going to restrict it to just a single control section. I did not, when we launched the assignment, we didn't understand how multiple control sections work, although this will be an opportunity to say, for maybe extra credit, being able to build a simple multiple control section solution where you can handle maybe 2 control sections, and you can build a simple ES tab and use define and refer records, might be something we can do as extra credit at this point. I am considering that strongly, but for the basic assignment itself, it's just going to be the basic, just the basic single control sections. Other questions?
So for the test, would we expect more code than in the previous exam? Like the previous exam was more technical, perhaps, on calculating operations. Would we expect more coding on the other hand, or?
That's a great question, Jamie. Yes, I will expect you to be working more with code in exam number 2. And that actually brings up a good point too about some of the differences between the in-class paper exam versus the online exam. Is that the online exam, of course, I will be expecting you to do your own work, but the reality of having access to reference material is that this is essentially now an open book exam, and I will be adjusting the format and the difficulty of the exam to reflect that. So in the answer, yes, you will be either writing code or modifying code, or you will be doing assessment of code to say whether something supports or doesn't support some capability, or rewrite the code so that it will assemble correctly and things like that. Yes, that would be expected. The exams also will be timed, so that will control some of and that's one of the things we do when we typically design an exam as to whether it's open book or not. We take into account the timing of it. Of course, in lecture, we can time it very carefully because it's there, but one of the tools I'm looking at also has timed restrictions on when you can see the exam and start providing answers and when it will stop accepting answers. So it will be time managed as well. No, I am looking at a browser lockdown option. I didn't say that specifically only because I haven't decided that that's the exact tool I want to use yet, but that is the leading contender. But having said that, the reality is I also know that a lot of students not only have a browser in front of them, but they might have a cell phone next to them. They might actually have a textbook, you know, those hard copy things that some people still buy, next to them, and some of them will have tablets and pads and stuff like that. I know how this works. Because, by the way, that's one of the things we do, right? We want you to be very smart students. That's one of the things that I tell people that I hire all the time, is that even after I hired them and they come with questions and stuff, it's like, wait a minute, we only hire smart people. So that's what we expect, and we expect creative solutions in a lot of cases. So I know that's how you think, because that's how we think, and that's a good thing. Of course, cheating is not a good thing. That's a whole different thing, of course, right? Other questions? So one of the things I'm going to do here next, and I'll keep watching for questions, but while I'm waiting to see if there's any others, I want to bring up chapter 4 briefly. We're not going to really go into it, but I do want to introduce concept here. Okay. So new share. Okay, so everybody should see chapter 4 now, yeah? And again, if you have other questions, go ahead and bring them in. Thank you, appreciate that. We can do that, but I would like to get into chapter 4 since we only have the 2 lectures, if there's no other questions. All right, so the idea with chapter 4 is we're going to take a look at macros. Now, I'm not sure what your concept of macros are. and what your expectations are of this whole topic of macros and why it seems to be deserving of a whole chapter. But if you start glancing through the material, you're going to see that basically it has its own parsing logic separate from what an assembler is doing that is worth studying because it's complex enough that it's going to take that much work for us to be able to support macros. And some of you might be thinking at this point of, well, if it's really complex and it's a lot more work, why do it, right? What is the trade-off? What is the benefit from implementing macros if we understand there's a lot more work to implement this? And the answer might not be obvious, and you may not understand an initial short answer, but over the course of study here, and as you start using macros, and maybe you've been using macros and you haven't realized you've used macros, that we find that having a mechanism like a macro as a convenience function for the programmer to use has over time demonstrated its utility. It has saved time. The macro is a way for us to be able to write instructions to the compiler, if you will, to say, do a bunch of work for me instead of me having to do some tedious repetitive work over and over and over again, with the likelihood that I'll introduce fat finger errors or just mechanical errors, or even errors that because I wasn't thinking through the process closely enough. There's lots of reasons why errors can get into our code, and the whole idea about having a compiler anyway, as you probably remember from your other classes, is that we want to create a language that is readable by us humans that the computer can understand. But in the case of the macro, what we're doing is we're telling the compiler to write code for us, right? It's a convenience mechanism for us to be able to tell the compiler to do that, because we understand, and that's what we're going to study in this chapter, we understand that the compiler can do this with a great deal of accuracy, and it can do it fairly quickly for us, right? So that's why the macro itself is important. So I know all of you have been programming now in C and C++. And when you use the pound include and the pound define, you're using two macros right there. Those assembler directives, those compiler directives in those cases, are shorthand for the compiler to say, hey, I want you to do some work for me. And by using those keywords for those specific macros, those macro instructions are then interpreted by the compiler to do some work before it ever starts actually compiling code. And that is, do this macro expansion, do the macro processing, macro expansion, in order to do work on our behalf as a programmer so that it can do it correctly and efficiently. That's what we're really talking about. You've been reading the words here on the slide. It's expanding on what I was talking about. That's the purpose of it. That's the concept behind it. Now, the ones in red, as you recall, these assembler directives in red for the SICK family machines are the ones that we already know. We're introducing two new ones, macro and mend, macro end, as two new assembler directives, two new assembler directives to enable us to be able to implement macros on the SICK family machines. All right, so a lot fewer in this chapter, but there's going to be some other work that we're going to do above and beyond. Okay? So let's go over the high-level definition then of a macro processor. And the high-level definition is what you see here, is that the processor needs to be able to recognize that we have defined macros here. We, the programmer, has created, by doing some macro definitions, some macros. And then the macro processor is going to need to save those macro definitions so that you can use it more than once, right? building a macro just so you can use it once is helpful, but building it so you can use it multiple times is valuable, right? So we want to be able to define a macro and then be able to save its definition so we can reuse it over and over again. And we'll see why that's important. You might not see the significance of that right now, but as macros do their expansion and they start creating symbols on their own, then it's important for us to be able to distinguish these two. I just realized I didn't have my pointer on. There we go. Be able to distinguish between these two. Okay, so having done that then enables us to be able to call macros more than once from our code that we're writing in the SICK family language. Okay, and then the assembler needs to then be able to recognize that macro, we're calling that macro, and then it needs to perform the macro expansion itself, or from the macro calls. Okay, because the whole goal here is that we're going to start with source code and we're going to generate object code. We've talked about the assembler or compilers in a higher level, and we've been focused on that in chapters 1 through 3, but now we're going to focus on this step in between our source code and the assembler, where the macro processor gets invoked, and then it's going to read and look and see if we've defined any macros or if we've used any macros, and it's going to perform this code expansion, okay, to replace that singular macro name with some assembly code to perform that work. So it's a great question, Marina, that right at this point here you might be thinking, well, what is the difference then between a macro and a function? And the difference is that, as you recall from a function, we're going to build a stack, because what's going to happen is during runtime execution, when we call that function, we're going to go to that memory location and we're going to return from that memory location at the end of that function to that particular next line of code at runtime. The macro processor is all being done at assemble time or compile time, where it encounters some macro that we want to use, and say, for this macro, what I want you to do is then generate 9 lines of code for me, or generate 17 lines of code for me every time I use this one macro name. So what we're doing is essentially, at a very, very high level, I should say, doing a code expansion based upon a single keyword, if you will, a macro name. From encountering this macro name, I need to generate these 17 lines of assembly code. Kind of a very high level definition of it, but because it's a lot more work to it than just that, but that's really what we're doing. Inline expansion versus code execution, which requires you to maintain a stack if you care about the value of the registers, which the rsub system call depends upon that linkage register. If nothing else, we worry about that. Whereas macroprocessors, there's no concept of that. It's just doing an inline code expansion when it encounters that name. That is true that functions, subroutines have return values, although sometimes you don't care about those. Sometimes you do, but they all have that built in. And yes, we're talking about doing inline code expansion with the macro processor, which, as you will see when we get into the discussion further, gets a little bit more complicated, because within our macro definition itself, where we create the macro, we can create symbols inside of the macro. And if we call a macro once, and we call it a second time, and we call it a third time, then those symbol names will still need to be unique. So the macro expansion is going to be a little bit more complicated, because as it expands, does this inline expansion of based upon the macro definition, the second time we call it, the third time we call it, it's going to have to build new symbols that are unique symbol names from the ones that are in the definition. So we're going to see how to do that as well. Excellent questions. Okay, that was the introduction to macros that I wanted to cover tonight, because hopefully that'll kind of get you kicked off for your readings this weekend, because we just have the next two lectures to go into the details of macro expansion that I need to go through, as well as your readings and assignment. All right, so any questions then before we call it a night? Okay, both the chat room as well as participants list looks like everybody's satisfied with what we covered. And yes, the exam will be on chapters 3 and 4. And technically, the exam is not going to be comprehensive, but as some of the chat comments have pointed out on Monday as well as tonight, is that it's kind of hard not to be somewhat comprehensive, only because we're using the SICK Basic and SICK XE machines, which means that it's going to be based on your knowledge of the machine architecture and the instructions and all those things that you know so far. And as far as midterm grades 1 are concerned, I can just go ahead and post what's recorded for exam 1, but I'm still reviewing, and I will have completed my review this Saturday. I want to do it by Friday, but I will have it completed by Saturday, and we'll have updates posted then. I've only taken this long because of two reasons. One is that the average score was much lower than I expected, and I see why now, and then I'm figuring out how I want to adjust it. We had this complication of shifting to virtual format here instead of in-class lectures that unfortunately caused me a delay as well. So I do apologize for that, but I think you can appreciate the need, I think, for doing both of those things. One is making sure that your GPA does accurately reflect your understanding of the material based upon the exam grading assistance translation of my instructions, as well as this delay. Okay, other questions? Excellent then. Okay, I will go ahead and do two things. One is that I will, for Monday's lecture, post the announcement for participation far more in advance than I did tonight. And two is I will, after this lecture, I will go ahead and save the recording, upload it to Blackboard as I did for the last lecture. Oh, that's a good question about reviewing exam 1. I'll have to get back to you on that. I'm going to have to look at how I can get those efficiently scanned and then uploaded into your Blackboard accounts, because that's the only way to provide copies of the written exam 1 back to you, is to do it in that format. So I'll take that as an action to figure out how I'm going to do that, but it is on me to make that happen and get that to you. I just don't know the time it's going to take for me to do that part yet. And again, the details of how the exam will be structured will be given once I've decided on which tool I'm using. But there will be a combination of types of question, and in this level of study, our 500 level study of computer science, we have a lot of what we refer to as prose style responses, which, as we mentioned earlier, a lot of that is going to be looking at code or writing code or assessing code and providing written responses to theoretical questions with some multiple guess or something like that thrown in there just to help. Okay, any other questions? Okay. Have a great weekend, and we will get some material out to you. Thank you for being with us tonight.
All right. Take care, everybody. Have a good night.